let us continue with the encoder-decoder architectures. And here, instead of a simple feed-forward linear encoder, I'm going to use convolutional neural network for image compression and reconstruction. So we are going to build this pipeline. First, a convolutional encoding, which goes from a spatial image data to a latent representation. And then the transposed convolution for decoding that goes from the latent representation to a spatial image. During this process, we see a progressive downsampling and upsampling, and we play with the compression ratios in this learned representation. I'm going to do this with the MNIST dataset. Okay, so here is some imports, and also I included a function that loads the MNIST dataset. So I will skip directly to the model. Okay, so basically we want to write the first part of this convolutional encoder-decoder, which is the encoder part. So let's call it conv-encoder. And like any other encoder-decoder architectures, we want this encoder to visual world. We see the details and then the shapes and the concepts behind them. So how we are doing it, we basically increase the channels or features while we are decreasing the spatial dimension. So we transfer or trade the spatial resolution for this semantic richness. We will add batch normalization for training stability. And here, notice that I'm using leaky ReLU to prevent dead neurons. So what we are going to get is this flow of information that through a few convolution blocks, we transform a grayscale 64 by 64 MNIST data into a latent vector of 128. Going to add the image size, which is basically the square image height and width. Here is 64. Note that in the load of the data set above, I resized the images to be 64 by 64. And the main reason is I want that to be a power of 2, as we are going to downsample and upsample. More specifically, we are downsampling 4 times by factor of 2. So we are looking at 64, 32, 16, 8, and 4. Okay, so what will be the final smallest image size in the encoder? We can compute this. It's the image size divided by, the plan is to do 4 times pooling, which means 16, yes. So that will be the final size, which then we will flatten into the latent space. Okay, so let's write the first block of convolution, which is a convolution, batch norm, a leaky ReLU. We will add another convolution here, and then another batch norm, and another leaky ReLU. Each block will have 2 convolution. First one keeps the size and normalize, and then get some nonlinearity out of it. And then after that, we will do the downsampling by 2, and then again normalize, and then activation. So we will repeat this 4 times. So the first one will be, like I said, it will be a bunch of steps. First, convolution takes in the channel and return 32, let's say, features, but we will keep the size for now. So for that, I'm going to have a kernel of 3 and then a stride of 1, and then padding will be 1. So for now, I'm keeping the image size. So that's why we need another conv here. Now we can reduce the size. So I'm going to keep the channel, but here I'm reducing the size, and the batch norm will get 32, and then we need another ReLU. That's the first block. Going to repeat this 4 times. I have to be careful about handling the channels. That's the only thing that we should be careful about. So now we basically flatten the output of this. So what did I do here? After the last convolution, I had a 256 4x4, and I flattened this. So I'm expecting a vector of this shape. But like we discussed, we want the latent space to be 128. So I have to add another linear. So a fully connected linear. Okay, that's the encoder. We have to have a forward method. Going to add that. Okay, so basically we have a forward pass through the encoder. It's always good to remind ourselves what was the input shape and output shape. The input shape is a 164 by 64, and output is a vector of latent dimension. And this is the rest of let's call this C. That's our encoder. Now we can move on to the decoder. So another class, which is a conv decoder now, and it mirrors the encoder, but in reverse, right? So it takes in the compressed latent code, Z, and reconstructs the original image. So here we have to write, instead of convolution block, we have to do a transpose convolution. Just a quick note on transpose convolution, which I want you to think about convolution operation. Convolution is, in fact, a linear operator that you can write it this way. I want you to think about this. Why convolution is a linear operator? So here, the matrix C is known as a Toeplitz matrix, a block Toeplitz matrix. And if you go to the D2L book, chapter 1410, you can read about transposed convolution. So there are some nice properties here about transposed convolution. For example, the transpose can be computed using backpropagation. So it's like basically another type of convolution. So I'm not going to dwell on this here, but you have to, of course, know the concept. Okay, so with that, let's write the methods. The latent dimension is 128. We have the output channels, 1 because the output or the reconstructed image is grayscale, and the image size is still 64. So some bookkeeping here about the image size. So I'm going to add a linear layer first that projects latent back to the from latent to spatial. So first going to write the inverse of the encoder's final linear layer. So if you remember, this basically maps the 128 vector to the 4096. Now we can write decoder blocks. So the first block, we need a sequential, just like before, a 2D convolution transposed, a 2D transposed convolution. So we will keep the same style, first upsample and then refine features. Okay, so note that I'm upsampling here. Okay, then we need the same normalization, same leaky relu, and here I'm refining the features, so I'm reducing the features. Okay, so that's the first block. Going to repeat this 4 times, and for the last dconv block, so note that I changed the name to dconv to be consistent with the encoder. I'm going to use a tangent hyperbolic to have a -1 to 1 output. Relu doesn't do that for me, to have the same bound as the original image. Let's write the forward method. The forward, we basically take in the latent vector and we are giving a torch tensor for the image. So first the vector, we view it like an image. So remember that this reshapes the latent to this spatial tensor of 4096. We want to send this to the convolution. So before that, I'm going to reshape it again to 4-dimensional tensor. Maybe it's good to explain it here. Okay, so that's how we are doing it. And then now I'm going to just call the decoding blocks that does the upsampling and feature refinement. Okay, so that's our decoder. Now we have everything to write our CNN autoencoder class. So here's the complete CNN autoencoder class for our MNIST data. We initialize the encoder and decoder as submodules. Okay, so then the forward method first compress to latency and then reconstruct from that latent. The methods encode and decode that basically encode the image to latent and decode the representation to image. Okay, so we have to train this. Let's write a function that basically train the CNN autoencoder, and the model is what is the CNN. We have the train loader, that is the data loader. Let's specify a number of epochs. 10 is fine. Learning rate, we will deal with it later. We have to define the device too. Let's put CPU for now as a default in case CUDA is not available. Okay, so model, remember that we have to send this to device. First of all, let's define an optimizer. So it takes in the model parameters and the learning rate. Okay, so let's write the training loop. Okay, so here I added some comments for you. And the only thing that worthy of mention is the calculation of the reconstruction loss, which you already know. Okay, so I added a visualization or a plotting function that basically shows the original and the reconstructed MNIST images for a few samples. Okay, so with that, we have everything. So here we have the loading. Okay, so then this is the script for our training. Just notice that I first look if I have CUDA. Then after that, I train for 5 epochs. I mean, in practice, you probably go for 20 epochs, but the data set is really easy. It's just MNIST data set, so it will be an overkill probably. I have an error somewhere. I forgot the Z, defining the Z. Let's see. Oh, here. Last one is C. Okay, so what else? Next error. Okay, there was an indentation error. Let's do it again. Okay. Here we have in-channel latent. So in-channel latent is probably here because the input of the convolution is latent and the output is in-channel. So let's check that here. Yep, so that's the reason. This should be here. Okay, so with that, let's try again. Okay, it is training. So while it's doing it, we can also ask for the visualization. The visualization takes in the model and some samples from the loader. So let me just add a note here. So the reconstruction, as you see, it's pretty good for MNIST, but we are not really expecting that reconstruction for more complex image data sets like CFAR, for example. And there are better ways to do reconstruction or even generative modeling for image dataset. Here, I want to have your attention for other uses of this Z or this compact representation. For example, one is basically just compression. So it's storing Z instead of the full dataset. We can do denoising, like we discussed before. We can do other interesting tasks like anomaly detection. We trained a autoencoder on digits 0 to 9, but whenever we see a high reconstruction error that flags a non-digit or maybe corrupted sample, we can also look at the similarity in style, for example, which digits are more similar by just looking at the distance between their Z vectors. Or maybe more interestingly, we can do tasks using these downstream features. So using Z as an input to a classifier, for example. So in that case, we can freeze the encoder and we can add a linear head and train that linear head for classification. So now this is not unsupervised anymore. It will be supervised. Another thing that can be interesting is to join these two losses, for example, adding the classification loss to the reconstruction loss. So we want an autoencoder not only reconstruct the image, but also it is very accurate in classification. So maybe that can regularize the other loss or vice versa. Of course, we can do classification using our previous CNN architectures, but here these are just some application of C that can be used in different data types too.